Hello. Today I will be presenting the article, The Typology of Ellipsis, a corpus for linguistic analysis and machine learning applications. And just to give a brief overview of today's presentation, I'll be talking about ellipsis constructions and their syntax. I'll be talking about our Hoosier ellipsis corpus, some evaluations and results, as well as a discussion of machine learning experiments. So, by ellipsis constructions, what we usually refer to is other common phenomena like gapping, sluicing, forward or backward conjunction reduction. So this entails the fact that lexical elements are elided under certain conditions. And native speakers have virtually no cognitive issues processing and understanding ellipsis constructions. But we note that it's not the case for other technologies such as LLMs or state-of-the-art parsers. So just to give a few examples of ellipsis construction, the first one here that we see is called forward conjunction reduction. This is basically an across-the-board movement. So let's take, for example, the sentence, my sister lives in Utrecht and works in Amsterdam. Here, the elided element is my sister or she as a pronoun. And to reconstruct the sentence, we have my sister lives in Utrecht and my sister works in Amsterdam. Another example is gapping. So if we take the sentence, Paul and John were watching the news and Mary a movie. Here we note that the elided element is the verbal element. So to reconstruct, that gives us Paul and John were watching the news and Mary was watching a movie. Note that the elided element does not need to be homophonous or share the exact same morphological information as its referent. So here we have were watching for plural and was watching, which is the elided element in the singular. Another example of gapping is will Jimmy greet Jill first or Jill Jimmy? And reconstructed is will Jimmy greet Jill first or will Jill greet Jimmy first? So here we see that the elided element can be multiple and in different places in the clause. Another example is discourse licensed ellipsis. So let's take, for example, two people, person A and person B, and we have the conversation, who wants to marry whom? And then the second person answering, Susan, Larry, in which the person just replaced the who and whom elements and did not repeat wants to marry. And finally, we note some semantic issues with ellipsis constructions. So let's take, for example, the sentence, John drove to Wisconsin and was arrested in Illinois. Here, the elided element, which is John, does not share the same semantic information or semantic role as its antecedent. So in the first clause, John is an agent driving. And in the second clause, the elided element, John still, is this time a patient. And finally, another example of semantic issues that we see in ellipsis constructions is with the sentence, Peter stole a book and John kisses from Mary. Here, the reconstructed sentence is Peter stole a book and John stole kisses from Mary. And here we see that the verb steal in the first clause and in the second clause, they do not share the same semantic meaning. And this is one of the issues that we run into when we run this sentence through a parser. So, regarding ellipsis constructions, there are publicly available datasets such as Sluicing Corpus for English by Anand et al. 2021, the VP Ellipsis Corpus for English by Bose and Spinatter 2011, and Goldberg and Stubbs 2020, and the LA Corpus for English by Testa et al. 2023. However, these datasets are relatively small and they are usually limited to English and a few common languages, and they are also limited to specific ellipsis phenomena, so either sleuthing, VP ellipsis, gapping, etc. So there is a clear lack of cross-linguistic typological overview of ellipsis types, and the explanatory theoretical analysis of ellipsis constructions do not necessarily translate easily to more practical applications. And the frameworks like dependency grammar, lexical functional grammar, and even generative framework like the minimalist program do not provide descriptive or explanatory means. So looking at the current state-of-the-art natural language processing pipelines and parsers, we note that they all perform poorly with elliptical constructions. So we tested the Stanford Core NLP, the Stanford Stanza version 1.6, the Berkeley Neural Parser, or BENAPAR, spaCy version 3.6, and XLE. And they all failed with ellipses and other constructions. So it's not useful for downstreaming NLP tasks, such as relation extraction. So here we give an output example of spaCy, version 3.6, with the sentence, John bought a book and Mary a newspaper. So here we note that the error in parsing is that Mary is a conjunction of book, meaning that the meaning expressed here is that John bought a book and Mary. And we see that a newspaper is assumed to be a modifier of Mary instead of the object of the elided verb whose subject is Mary. Another example of the sentence I talked about earlier, so John stole a book and Peter kisses from Mary. So the Berkeley Neural Parser shows that the noun of the object, kisses, is assumed to be the predicate head of the second conjunct. So here kisses is considered as a verb and not a noun or an object. And so here we see that it fails at parsing correctly the elliptical construction. So with regard to computational tests, we looked at the closed test, which is usually used in machine learning for marked word prediction in BERT, for example, and next word prediction as in large language models. So the tasks were, we had 3 of them. The first one was classification of sentences or utterances as containing ellipsis or not containing ellipsis. The second task was about detecting the place and location of ellipsis in the clause. So we asked the models to indicate where the ellipsis or elided element is. And finally, task 3 is about guessing the missing word, so filling the gap and fill in the, like reconstruct the elided sentence. So for our experiments, we collected a corpus of elliptical constructions for 18 languages with varying number of examples. So the largest are Arabic, Mandarin Chinese, Croatian, English, German, Gujarati, Hindi, Japanese, Kumaoni, Korean, Navajo, Norwegian, Polish, Russian, Spanish, Swedish, and Ukrainian. And we're preparing examples for Bengal, Hebrew, Kannada, Tamil, and Telugu. And we tested language models and parsers on English, Arabic, Spanish, and Russian. So for the experiments, we picked 500 target sentences and created 1,000 destructors. And for tasks 2 and 3, only examples with ellipsis were used. And the algorithms that we used was logistic regression to use as our baseline. And we looked at BERT or the Roberta-based deep learning algorithms. We looked at GPT-4 large language models such as Falcon, Llama, etc. So with regards to our corpus access, we we'll make our corpus available and open source in the next few days. And here you have the link to our GitHub repo as well. So looking at the experiments in particular, so for Arabic, we utilized GPT-4 and no other large language models because they were not able to process Arabic. And we are missing a useful word type language model for Arabic. And so we intend to train one at some point in the future. So for our first task, the zero-shot classification, our baseline logistic regression algorithm had an 83% accuracy compared to GPT-4, which had a 72% accuracy. So GPT-4 did not beat our baseline. And then looking at task 3, for task 3, we only looked at GPT-4 results. So in a zero-shot word filling context, we had an accuracy of about 80% for Arabic. Now looking at English, we see that GPT-4 yielded the best results, but still under the results of our baseline model for task 1. And for task 3, we noticed that GPT-4 had an accuracy of about 25%. So to look at the details of the English experiment, so the logistic regression is a supervised training method, and the training included 1,600 sentences, and 50% of them were ellipsis constructions. And for task 1, we had an accuracy of about 74%. And this can be improved with a few more features, including unsupervised feature generation. And so looking now at the zero-shot classification, we asked the question, does the sentence contain ellipsis? To GPT 3.5, GPT 4, Llama 2, Zephyr, and we're currently working on Cloud 3. So here are the results for each of these models. And so we noticed that looking at the accuracy, GPT-4 yielded the best results out of the 4. So we see that the supervised machine learning or NLP methods outperform all large language models on zero-shot. And we know that GPT with the default temperature randomizes 20% of the output decisions, which means that for 20% of repeated tasks with the same data, the classifier will be switched. And using GPT with temperature set to 0, we see that there's no random decisions, so it's deterministic, but we note a drop of accuracy by 10% over sample data. So looking at task 2, we tested 3 large language models, so GPT 3.5, GPT 4, and Llama 2. And for task 2, we see a drastic drop in accuracy for all 3 models, with GPT-4 that has the highest accuracy of 15%. And some of the issues that we've identified was probably due to prompt engineering and instructions, as well as the evaluation and the position matching. Looking at task 3, we note as well that GPT 3.5 and Llama 2 have a 0% accuracy. GPT-4 has a 25% accuracy. So these results are still very low. And the issues that we haven't identified were related to the need for more experiments with prompts and improving prompt engineering, maybe, and looking at string matching evaluations. So to recap, for English, looking at task 1, we see that the logistic regression, our baseline, had an accuracy of 74%. The BERT-based transformer had an accuracy of 94%. GPT 3.5, 35%, and GPT-4, 60%. So we know that the BERT and transformer models outperformed logistic regression, which itself outperformed GPT-4. And this came as a surprise because we know that there are problems with invisible words in all parsers, but also in LLMs. and the parsers perform without a problem with ellipsis undone. So the problem is, first of all, theoretical, because there is a lack of practical transfer of the theoretical frameworks that deal with elliptical constructions. And looking at dependency grammar, lexical functional grammar, we see that in the parsers that are built off of these. The problem is also data-based. The fact that there are a lack of corpora with annotated ellipsis constructions across the board and cross-linguistically. And the problem is also computational, and the fact that large language models predict next words and not next missing word, like what BERT and the transformer architecture does with mask word. And on this note, thank you.